All right. Welcome to the second installment of our winter seminar. So today we have 4 great student speakers. We're going to start with Adam, and then Alex, Kristi, and Carl and Kristi. So these are all students that we're highlighting because they're going to TRB, and besides submitting a paper, they have been selected for a presentation. So just to remind you, if you're a student or if you are not, you should be always touching here and make sure you have the red button so people online can hear you. And if not, just let us know and we'll give you the mic. All right? Thank you. And we'll have questions at the end of the 4 presentations, so save your questions.
All right. Hi, everyone. My name is Adam Moore. I am a grad student in civil engineering. I work in the Intelligent Transportation Systems Lab over in the engineering building. Today I'm going to be presenting on the topic of my master's thesis, which is air quality at bus stop shelters along a busy urban corridor. In this case, we're looking at Powell Boulevard, for those of you familiar. So why are we looking at air quality? One of the things with different modes of transportation is that they're highly dependent. Exposure to air pollution is highly dependent on the mode of travel that you choose. So if you're in a car, a bike, public transit, or if you walk, it's going to affect the level of pollutants that you are exposed to as you commute to work or to school or whatnot. We've chosen to focus on public transit, which is something that has been studied a lot. A lot of studies have looked at exposure, particularly inside buses as you're traveling from point A to point B. Very few studies, though, have looked at the initial leg of travel, which in this case focuses on while you're waiting at a bus stop. What this means is maybe you're standing right next to a busy road for a very long amount of time, and so you're right next to vehicles as they pass by. So that's why we're looking at air quality in this context of transportation. What we're focusing on within air pollutants is particulate matter. Why particulate matter? It's been linked to elevated levels directly next to roadways, so we know that vehicles are a source of particulate matter. What it is it's a mixture of solid and liquid material. It's similar to an aerosol or a gas. It's very, very superfine particles made of carbon, hydrocarbons, and inorganic material. It's a non-threshold pollutant, which means that no matter the level, it's a harm to your body. So there's no level that's safe to be around when it's concerning particulate matter. It's carcinogenic. It's been linked to heart disease and higher mortality rates, and it increases respiratory disease incidence. It's generally classified into 4 categories, and these categories I'm going to be discussing further as we go on. PM10, 2.5, 1.0, and UFP. PM10 means that it's got a diameter of 10 micrometers, and you can see here I have just a little diagram to show you the size discrepancies between the 4 sizes. UFP, ultrafine particulates, are incredibly small. They are the most dangerous because of their size. They penetrate the farthest into the body, so they bypass a lot of the body's natural defenses and get way deep into your lungs. What we've done is we've focused on bus stop shelters, and we did that because bus stop shelters typically signify locations where a high volume of people are waiting at next to the roadway. Typically, you have 50 boardings per day. Signifies that you need a bus stop shelter in that location. So we know that a lot of people are waiting right next to the roadway. For this study, we focused on Powell Boulevard. We found that there, along a 2-mile stretch of roadway that we singled out, there were 31 bus stops, 17 of which had bus stop shelters. We picked 3 of those, and we categorized them by a variety of things. The main thing we were looking at, though, is which way the bus stop shelter is facing, so if it's facing towards the road or away from the road. And we characterized that based on the opening. Bus stop shelters typically are made of 3 plexiglass panels, the opening which people get in to wait. So the 3 shelters that we looked at, the first one here, I've made this little diagram to show, which is very hard to read, but I'll point out some things on here for you. This is where our bus stop shelter is. This is Powell Boulevard running east-west. We have commercial buildings here, and a 4-story apartment complex right here. Across the street is a parking lot. That shelter is facing away from the roadway. This shelter, located right here, is facing towards the roadway. Again, there's a 3-story school directly behind it. There's a park here, residential here, and then business right there. Here we have, again, Powell Boulevard running east-west. The shelter this time is here with a 2-story grocery store right behind it. It's facing towards the roadway. If you can see what we did here is we tried to pick shelters that have similar built environment characteristics to be able to control for a lot of different variations. This shelter is significant, though. I'd like to point out that across the street is a gas station, which we'll get into in a little bit why that matters. So how we collected data. We did this out in the field. We collected our own data. We had 3 different things that we looked at: particulate concentrations, wind speed and direction, traffic volume and classification. Particulate concentrations, and I should say we measured twice a day, in the morning from 7 to 9 a.m. and in the evening from 4 to 6 p.m. We did this twice at each of those shelters that I just showed you, so for a total of 8 data collections. We put the monitors inside the shelter to measure particulate concentrations just inside the shelter, and we also put a monitor just outside the shelter. It's sampling at about 5 feet inside and outside the shelter. This way we're able to compare, simultaneously we're able to compare levels to make any conclusions about particulate concentrations. We also were keen to look at wind speed and direction. This is the sonic anemometer, typically placed just next to the outside location. And then finally, we looked at traffic volume and classification using this device up here. It's known as an RTMS unit, is the model that we were using. It's capable of counting the vehicles as they go by and also measuring their length, so you can make assumptions on if it's heavy trucks or passenger vehicles going past. The problem with our RTMS unit is that it was only capable of measuring the closest 3 lanes, 2 to 3 lanes. So we, in essence, were only able to capture one direction of travel, which really means we're only looking at half of the roadway usually. So we had to take that into account. So to get straight to the results, we were able to show that, typically speaking, for a shelter facing away from the roadway, so that first shelter I showed you, what we have here is, this is our morning sampling, and these are our particulate concentrations here, ranging from about 20,000 to about 100,000, and this is for our ultrafine particulates, particulates per cubic centimeter, I should say. So we were able to show that this dashed blue line, which is the outside, is usually higher than levels inside the shelter. In other words, when the shelter is facing away from the roadway, you have less particulate matter inside the shelter than you do just outside the shelter. In contrast, when the shelter is facing towards the roadway, the other 2 locations, it's the opposite. It's usually, you see a higher concentration inside the shelter than you do outside the shelter. So it's acting as a trap. It's holding in the particulates. We found that there was a statistically significant difference between the inside and the outside. Going back to those 4 sizes of particulate matter, we found that when it's facing the roadway, there is a pretty big difference between inside and outside, ranging from about 12 to 21% greater inside the shelter. When it's facing away from the roadway, it was usually greater outside the shelter, not by as large a magnitude, but still very interesting to look at. Even when it is greater inside, it's still less inside than out than when it's facing towards the roadway. This was interesting. We didn't really expect time of day to be an issue necessarily when looking at this, but we did find that it was the most influential variable. Mornings were typically much greater magnitude of concentration than the evenings. So in summary, when the shelter faces the roadway, it's greater inside. When it faces away from the roadway, it's greater outside. And the mornings are generally greater than the evenings. We also were able to tack on vehicle flow to the particulate concentrations to look for associations between. Hopefully, we were able to find that heavy vehicles, when they pass by, we saw an increase in the particulates. We did not actually find that, though. You can see sometimes the particulates noticeably follow the vehicle flow, but there are other times, where it's jumping up and down, and you don't see a whole lot of association, and that was held up in the statistical analysis that we ran. Wind speed and direction were measured, although we didn't include those in our statistical analysis because there's just a lot of discrepancies with the way wind behaves in small microenvironments. To explain this real fast, the circles measure wind speed, and the angular coordinate measures wind direction. So let's say this point right here says that when the wind is blowing in the east and it's 2 meters per second, we get roughly this concentration of ultrafine particulate, which corresponds roughly with about 3,500. I'm sorry, 35,000 particles per cubic centimeter. And we didn't see a whole lot of differences between inside the shelter and outside the shelter, although there was a little bit worth looking at that we got into. And we were really able to say that the shelter, depending on which way it's facing, either holds in the wind, which means that the wind is bringing in more concentration, or if it's facing away from the shelter. But that was mostly dependent on the buildings that were right next door. If it's right next to the building, then obviously there's not much wind coming through right there. So just to go over the conclusions we made, the shelter orientation is important. It does matter which way the shelter is facing. This is kind of important because air quality is not really a factor in bus shelter orientation for transit agencies. So maybe it's something that they could be looking at. If they place the shelter away from the roadway, then they could be helping waiting passengers in terms of their exposure. This is one of the first studies to have looked at bus stop shelter orientation. And we have a little more work to do to look at such a complicated microenvironment, wind measurements mostly, but we also need to look at make sure that our shelters are exactly the same. The first shelter, the one that's facing away from the roadway, actually has shorter walls. It's just the way TriMet does their shelters, and so we weren't able to find one that looks the exact same as the shelters that face towards the roadway. So I think we're going to hold questions till the end, but I'd like to acknowledge OTREC and my advisor, Dr. Miguel Figliozzi, Dr. Chris Monsier, and Eric Albright and Courtney Slavin for helping with my data collections. And that's that. I gotta give you this.
All right, we'll try and make a quick transition here. I'm also going to be talking about some air quality stuff. I wore a tie today for my microphone and for looks. All right, so my name is Alex Bigazzi. I'm also a graduate student in civil engineering, working with Dr. Miguel Figliozzi on this project. So like I said, looking at emissions and air quality issues as well, but on the opposite end of the scale, looking at from a very macroscopic perspective. The question that we will ask and answer today is, do mobility-based and congestion-related performance measures reflect macroscopic emissions trends? So a little bit of motivation for that. We know congestion is increasing. It's pretty well measured and documented worldwide. And there's also a body of research that shows that higher levels of congestion can be associated with higher emissions rates per vehicle mile of travel. All right. But what's not so clear is the relationship between congestion and total emissions, so including not just changes in emissions rates per mile of travel, but the volume of travel, but the number of vehicle miles traveled, and that's VMT. And this relationship that's been shown between congestion and emissions rates has either led to or contributed to a pretty strong association in people's minds between congestion and emissions. And so but because of this uncertainty between congestion and total emissions, we wanted to take a look at that, see if that association still holds when you're looking at total emissions on a macroscopic scale. So the research questions that we'll be looking at today, first of all, do congestion and mobility performance measures reflect macroscopic emissions trends? And then if not, what transportation-related measures can we be looking at to better understand emissions trends and performance? And this is motivated not only by the association people have between congestion and emissions, but also by the fact that it's hard to measure and monitor emissions. Technically, it's difficult to do, and so the widely measured and reported transportation performance measures, if they can be associated, it would be a convenient proxy for the environmental performance of the system. So our methodology for looking at this, we look at correlations between emissions estimates, they are estimates, and several different transportation-related performance measures. We do it at the metropolitan level, which is the bulk of the presentation today, looking at cross-sections of metro-wide averages, as well as trends in a couple cities. and then finally at the corridor level using much more detailed data for a comparison at different scales. So the transportation performance measures we're looking at, there are a number of them. We look at average speeds and travel time and reliability of speeds and travel time. And these are normalized to travel volume. So these are measures like the travel time index and the buffer time index, if you're familiar with them. So they're sensitive to changes in the speeds, either average speeds or variability in speeds, but not sensitive to changes in VMT. We also look at congestion extent in terms of percent congestion, percent of roadways congested, percent of travel congested, et cetera. And then finally, the amount of travel. So this is just a quantity measure, VMT, vehicle miles traveled, and VHT, vehicle hours traveled. Traffic data we used for these performance measures. For the metropolitan level estimates, we drew our data from the Urban Mobility Report. Now, if you're familiar with it, if you're not familiar with it, the Urban Mobility Report is certainly the widest cited mobility study in the United States. It comes out every year, receives a fair bit of attention in the press. And from the data tables accompanying the Urban Mobility Report, for every year back to 1982, we were able to pull a lot of metropolitan-wide performance characteristics. So peak period, average peak period speeds on freeway and arterial facilities, vehicle travel volumes, the number of peak period travelers, various congestion performance measures. And they draw these data from a number of sources, including highway performance monitoring and National Household Travel Survey data. So again, these are metropolitan-wide averages, so they involve a number of simplifying assumptions. So by pulling these data, we are also making a number of simplifying assumptions, as you can imagine, for metropolitan-wide averages. So to kind of contrast that, we also looked at a corridor estimate using much more detailed data. So we used the Portal Data Archive, which hopefully a lot of you are familiar with. It's our data archive here at Portland State University. And we pulled 3 years of data for 14 miles of the I-5 corridor going all the way through town. So we pulled vehicle counts and vehicle speeds at hourly aggregations for 3 years. For the emissions estimates, we used the MOVES motor vehicle emissions model, which is the standard right now in the US for macroscopic emissions modeling. Now, the emissions rates that we use, they're a function of average travel speed as a level of congestion, and they're also a function of the facility type, so freeways versus arterials. But we did not vary them for vehicle fleets or vary them over time. So we're just looking at changes in relationship to changing traffic conditions, not looking at the larger trends related to emissions. And I can explain later, if there's time, that that actually is a conservative assumption with respect to our results. And then finally, the last methodological point, we estimated it for 5 different pollutants. CO2e is greenhouse gases and carbon dioxide equivalents, carbon monoxide, nitrogen oxides, fine particulate matter, and gaseous hydrocarbons. So, moving on to the pretty slides. This is a cross-section where each point is a city, and we have them segmented by city size, and this is for the year 2010. On the vertical axis, we have the estimated total peak period emissions for the city. And on the horizontal axis, we have TTI, which is the travel time index, a widely reported measure of mobility. So in general, you can see here that the higher travel time indices, the farther we go on the right, the higher values we see for total emissions for the city. But if we break that apart and look at it by city size, if you look at it stratified by city, you don't really see an increase with the congestion level, with the travel time index. And it's because it appears from this that the higher levels of emissions are more related to the size of the city than the level of congestion in the city. So to look at it a different way, we average the city's total emissions by the number of travelers, divided by the number of travelers. So this is, on the vertical axis now, we have average daily peak period greenhouse gas emissions per peak period traveler, per person traveling. And then, again, our TTI mobility measure on the horizontal axis. And you can see here virtually no relationship. All right, so once we're controlling for the number of peak period travelers, kind of a proxy for the size of the city as well as the level or the amount of economic activity going on or the amount of travel going on, there's no relationship between average daily emissions, and our mobility measure. And this held for our other volume-insensitive mobility measures as well, such as the commuter stress index and some of the congestion extent measures. And the only place we found a relationship is with our performance measures that related to the total amount of travel. So here we have the same thing on the vertical axis, per traveler emissions, and on the horizontal axis now we're looking at vehicle hours traveled per peak period traveler per day, and we see a strong correlation here. So again, the mobility measures, which are insensitive to volume, not really a relationship with emissions, whereas we do see a strong relationship when you're looking at the total amount of travel. So to pull a lot of these together, here's a table of correlations. I kind of have them color-coded. On the left here is a bunch of different measures. So the dark colors here, we see total emissions are correlated with total amount of travel and with basically the size of the city, but that a lot of these other congestion-related, mobility-related measures, while there's some moderate correlations with the total amount of emissions, once we control for the number of travelers, only VMT per traveler and VHT per traveler are strongly correlated. We looked at trends also for the city of Portland, and I won't dawdle here too long, but simply to show that the emissions, again, are tracking with VMT and VHT rather than the TTI, which is our mobility metric. Looking at the quarter study, I don't have time to get into it in this presentation, but essentially it showed the same results, strong correlations between emissions and VMT and VHT, but weak or no correlations with our speed and congestion measures. And then with at the quarter level, we are able to look at reliability measures, and also not a strong correlation. So mobility and related congestion performance measures do not reflect emissions trends at the aggregate level. Again, we're looking at fairly wide averages here. And if we're looking for transportation system outputs that we can associate with emissions trends, we're better looking at the volume of travel, either in terms of the number of miles, the number of hours traveled. So in a sentence, mobility measures should not be associated with emissions performance for a city. And don't ask me any questions yet. So, thank you. Is that you?
Yep. I don't need the tie. I needed a tie. I didn't get the memo. Okay, so my name is Carl Olson, and I will be presenting on a framework for multimodal arterial data archiving. This will be presented at TRB on Tuesday, so if you're there, be sure to stop on by, check out the expanded version of the presentation. So to introduce this topic, first I'll tell you a little bit about Portal. Alex mentioned it in his presentation. Portal is the region's transportation data archive. Currently it stores freeway loop detector data, weather data, and incident data, and then it provides some sample visualizations for this data, given speed flow. You can check out the weather, some other features that are there currently. But our goal for this particular project is to expand on that and not just have the freeway network data set, but also include multimodal arterial data. This can include anything between bicycles, automobiles, buses, pedestrians. And then we want to create a web interface to allow people to visualize this data, but also make it accessible to people wanting to do research, to easily download the data in its raw form, and then expand on it from there. So in storing data, first it's always good to set up a framework, how you want to store this data, but also how you want to relate it to other types of data. If you can relate vehicle data to pedestrian data and maybe find some sort of connection there, it's important. But to do this, you need to have an efficient way to store the data. And then you also want to make sure it's not replicated. Having replicate data can cause some serious problems down the road. And then, like I said, relating the data between different types of sources. And then robust metadata. Metadata would be data explaining the data. It doesn't do you any good to have massive storage files of data if you actually don't know what that data means. And then having a way when the data is loaded into, say, a database to catch any type of problems that you may have. be it errors, bad data, duplicate data like I mentioned before. So when we first started with this problem, we had to think about, well, what are some of the data types that we might have? So this is just a simple road arterial segment. You may have traffic signals. So you may have traffic signal data, difference between maybe what phase is currently active at any given time to the instances of max screen. You may have vehicle data, so volumes, possibly occupancies, how long that particular detector was occupied. You might have bus data, so anything from the amount of stops, people getting on and off at that particular stop, how many times it was served throughout the day. You might have bike data, so the amount of bicyclists taking that particular arterial network. And then finally, pedestrian data. If you were here last week, Sarisha presented a little bit on this. This would be maybe how long it takes for a pedestrian to be served at an intersection, or the number of actuations per particular time segment. So if you have all those different types of data, finally, Bluetooth data. Bluetooth data would be, I'll discuss it in a little bit, but it's anytime we might read a Bluetooth device, we could match that up with another Bluetooth reader downstream and get maybe travel times or average speed for that particular segment. So when you have all those different types of data coming in from all different types of sources, you want to start to maybe relate it. And so one such way is relating vehicle detectors maybe into stations. So if we grab two vehicle detectors, say going northbound, and we can group those together by stations, it kind of creates the first step of relating all the different types of data together. The next one's a little more bigger, and it would be grouping things together by intersection. So anything that's related to that particular intersection, you may want to group together. So if you're curious on all the different types of data that might be available for this intersection, you may select that intersection, and then you can get back all these different types. Or maybe you're curious about a corridor. You want to know anything that might be available for, say, the 82nd corridor. You want to know any type of travel times, volumes, anything that you can obtain. So once you have that, this is kind of a simpler version of what I just discussed. Detectors, individual detectors that are either recording cars, bicycles, you may group those together in stations. And then those stations could belong to either intersections or corridors or both. And this is probably more of the data junkie side. If you're into database management, this is how it was set up as far as the bold is the primary key for this particular relation schema, and then the arrow indicates the corresponding key that relates to the next table. So station ID is located in detectors to show that there's a relationship between detectors and stations. Stations can also be related to either intersections or corridors, and they have the corresponding intersection and corridor ID. Stations would include information like the latitude and longitude of that particular station. So if you wanted to know exactly where it's at, we have goals of making this accessible via a map so you can select by area. Latitude and longitude is important for those types of things. So I had briefly discussed earlier some of the data sources. Currently, here are some of the data sources that we're archiving and starting to archive here in Portland. We have vehicle detectors located all throughout Portland. They're typically located 300 to 400 feet upstream or downstream from an intersection. They record volume, and some of them are recording occupancy. It's not the greatest of data right now as far as occupancy. It's a little messy, but we are definitely getting volumes, and these are recorded on 1-minute segments. We're also getting some interesting traffic signal data right now. We get it's a quite robust data set, very large. It has a line item or a piece of data for every single time that the phase changes on a light. So that could be any time when a red changes to a green changes to a yellow, and back and forth. But that's for all directions of that particular intersection. And every single time there's a line item or there's a change in phase, it also lets you know if there is a call, be it a pedestrian call or a vehicle call, and what particular segment of that particular intersection is making the call. And then last, it also records the timing plan that's currently active for that particular intersection. And then you can use that to determine if maybe your corridor is coordinated or if it's acting in a free flow state. And then, like I had mentioned, the data is stored per each phase change. And then we have transit data. This is a very robust data set provided by TriMet. It provides anything between automatic vehicle locating, so we can know exactly where the vehicle is, to passenger counts, the amount of people boarding and alighting from the bus. It records the departure and arrival times at all the different bus stops, how long it's been sitting at that bus stop, the number, like I mentioned, people getting on and off, and then there's even more data beyond that, average speed between bus stops. And then bicycle data, we're getting volume data at various locations throughout Portland using loops, kind of like this guy right here, usually in advance of the stop bar. Pedestrian data, number of actuations and delay that the pedestrians experience between when they first push the walk button to when they are actually served. And then finally, Bluetooth data. The Bluetooth data captures the MAC address. It's then truncated for privacy and records the date and time that that Bluetooth was read, and then that can be matched up downstream when it gets a similar type of reading, and you can kind of, from that, you can estimate travel time and average speed and maybe origin and destination patterns once we have enough Bluetooth devices set up around town. So, we're storing all this data, but we wanted to see, okay, what are some uses that we can actually do with it? So this particular graph is for a station, so a set of vehicle detectors heading northbound. It's on 82nd and Burnside. It's for Monday through Fridays in the month of February in 2011. So all of the gray lines indicate all the different days within the month, but the black line I've bolded out, and that's for the 8th of February. And we notice that it doesn't follow, it follows the trend all the way up until about a certain point at about 10 o'clock, and then there's a spike in volume. And so we're curious, okay, what could have caused the spike in volume? So we went over to Portal, which is currently up and running, and we noticed that there was a significant decrease in speed and volume around that same time. So we're like, okay, that's interesting. Maybe people were diverting off of I-205 northbound and using 82nd as an alternative route. So we went ahead and explored it a little further. And what we found was that there was an incident that closed all of the northbound lanes heading northbound just north of the Powell Boulevard exit. And this caused many of the vehicles to exit the freeway and use the arterial as an alternative means of travel. Well, what that could mean for us is these numbers at the top signify the timing plan that's currently active. Well, we have an evening timing plan that usually kicks on at 3, but if this was live data and someone working in, say, an ITS lab for the city of Portland saw that this was happening, they could possibly turn on signal timing plan 3 for this corridor to better facilitate this increase of automobile traffic and hopefully improve flow throughout that corridor as kind of an accident management type plan. So going through this, we ran into a couple things that we learned. There's a real need for multimodal data. I mean, having a one-stop shop or one location where you can get all the different data is incredibly helpful. Currently, this data is not being stored long-term. The city of Portland, after 90 days, their data, they just erase it and continue to override it. So we've been collecting, for example, the loop data for now over a year and a half, and we'll continue to expand that. And we're looking at setting up a real-time data feed so it doesn't involve that human middleman element. Another important thing is if you set up a framework, it needs to be flexible because you're not sure what types of data you may be getting in the future. And so you need to be able to alter your current framework or at least provide, when you're setting it up now, the ability to change things around if necessary. And then, of course, going out and actually talking to people who may be using this, you want to know what their end product, what maybe some graphs that they'd like to see, and then so you can set up your framework to easily facilitate that need. And then our final future work is to integrate it with Portal. We are currently in the process right now of setting up data available, plots, and then you can actually go online if you're curious. You can go online to portal.its.pdx.edu and check it out. The highway data is definitely available, and soon the arterial data will be as well. So, thank you.
Thank you. So I'm going to be talking about something a little bit different. I'm going to be talking about land use and how it relates sort of to transportation. Specifically, I'm going to be talking about Institute of Transportation Engineers trip generation manual and the rates that they use, and a methodology that we use to adjust that for urban context. So the Institute of Transportation Engineers, the ITE trip generation manual, is essentially a large data set of estimates of vehicle trips to different types of land use. So what we have on the right is a high turnover sit-down restaurant, something like a Pizza Plates or a nicer burger joint. And here, data points taken from all over the United States over several years have estimated the number of vehicle trips occurring at that establishment based on the square footage, the size of the establishment. Engineers and planners use this in traffic impact analysis to account for how much burden new development will place on the facility network surrounding it. So an establishment that brings in lots of vehicle trips will have a higher impact on the local facilities, and the business will need to account for that. The limitations of ITE trip generation include that the context that these data points were taken out of are typically very vehicle-oriented, single land use suburban sites. And the limitations of this mean that when you start integrating more urban context, density, access to transit, things like that, these estimates from ITE are overestimating the amount of vehicles to these land uses. Oh, I had that in there. So the correct estimate would be much lower than what ITE trip generation is actually estimating. Jurisdictions recognize this as a problem, and many of them have sort of roundabout ways of dealing with this. Some require that all new developments that are in any sort of urban context do their own data collections to predict mode shares and things like that. Other jurisdictions try and keep a log of what's been happening in the past so that they can have a better idea of how much lower the estimates would be compared to ITE trip generation. But there's really no generalized way of handling this throughout the United States. And as a result, traffic is being overestimated to new facilities, and they will have to account for this and pay impact fees and account for that in the cost, so they're paying for generating more traffic than they actually are. And so in our research, we wanted to look at using available data to develop a regional context-based methodology where we can account for urban context in adjusting ITE trip generation vehicle trip rates for all non-vehicle trips. By using the available data that we have, there's no substantial cost for new data collections, like when you have individual data collections for each new development. And by adjusting ITE trip generation, we're not throwing away a substantial amount of data that is considered an institutionalized practice among many jurisdictions. So for our methodology, we assume that the person trip rates accounted for in ITE trip generation don't vary with urban context. But the mode splits of these contexts, or the mode splits of these places do vary with context. And what that means is that while ITE trip generation may overestimate vehicle trips in more urban contexts, they do account for person trips. And then also that they may be that calculating the correct mode split in urban context can be applied as a reduction to the vehicle trip rates in ITE trip generation. And so in our methodology, what we do is we consider the context in which trips are taken, the transportation environment, the built environment, and socioeconomic variables, and we compare people's travel choices that they make. And specifically for this study, we're looking at what mode people take. So for our data, we used a household travel survey taken in Seattle, and we looked at each trip that was taken, which was about 87,000 trips. We considered the mode choice that every person took on every given trip, and then some other variables to characterize the type of trip, the trip distance, the time in which it was taken, some information about the person, what sort of income they have, their gender. And then we also took out specifically shopping, dining, and personal service trips because we wanted to focus on one specific type of land use. And then finally, we looked at the context in which the destination was taken. And by context, we define this as the built environment. So we looked at census-type data, Tiger data, and we collected 7 variables for every one of the 87,000 trips, destinations. And from these 7 variables, we did a clustering analysis to define 8 specific contexts that we found in and around Seattle. And these 8 contexts ranged from the suburban area to dense residential area to a central business district type area. And we use this context to define within every trip. We then took all this information for every trip that was taken, and we estimated in a model the likelihood of arriving at a destination having not taken a vehicle. So that may mean that they took a bike, they may have walked, they may have taken transit. What really matters when comparing with ITE trip generation is how many vehicle trips were not taken in a specific urban environment or context. And so what I have here is the estimates of the models. On the left side, we have the 8 contexts. We provided them names to give you an idea of description of what you're seeing. The higher up is the more urban context. This is your very dense CBDs, much more employment, and then as you go further down, it's more suburban, more similar to ITE trip generation. What we found, controlling for all those things, trip distances, household income, was that the more urban you get, the more likely you are not to take a car or an auto in any way. And so what we did here is we wanted to see how this validates with establishment type surveys. And so we found 27 establishment surveys that were the similar land uses, the dining, the personal service, and we found their non-vehicle mode split to overlay. And so this observed data is the 27 establishments that we found in California, where we took their built environment data, classified them into one of these 8 contexts, and then overlaid the range of non-vehicle mode splits that we were seeing. So our model that we estimated the likelihood of not taking a vehicle for most of the contexts where we had data was a conservative estimate of a range that you would likely see in that context for non-vehicle mode splits. The way that the data broke out when we were classifying was that of the 27 establishments that we found and surveyed in California, they varied in how they were placed. So there were no suburban or exurban sites that we had studied in California or that we had found in California that fit into the context that we outlined in Seattle. So the main findings of our research were that reductions to IT trip generations can be estimated based on the likelihood of non-auto mode splits occurring for any given person trip. So that means in the graph previously that the estimates from our models were conservative estimates of what we're seeing in the real life and may be used as a foundation for allowing for reductions of IT trip generation. We also found that non-auto mode splits are substantial and they vary across environmental settings. And that sort of leads into our third finding that any adjustment that we make to IT trip generation does need to consider the built environment and the context in which it was taken because these non-auto mode splits were substantial and are not currently being accounted for in IT trip generation. For our future research, we would like to look at using multiple household travel surveys from different regions so we can test the applicability across several regions. And we would also like to test our assumption that ITE trip generation does a good job of estimating person trips instead of just vehicle mode trips. And we could possibly do that by including additional establishment surveys, more than the 27 that we looked at, to help understand the variation that we're seeing. And then we would also like to look at accounting for the impact of micro variables like bike lanes, transit access, things like that, to look at the variation within each of the contexts that we were seeing. And then I'd like to acknowledge OTREC, Portland Metro, and ODOT for helping fund our study. Any questions? I guess we can ask questions now.
Adam, you're in charge of picking people.
All right, you want to go first? So on your talk, you said you pointed out the gas station across the street for shelter, and you said that that had some significance, but I'm not sure you came back to what the significance was.
I didn't. You're absolutely right. The reason I pointed out the gas station is that it's known as a point source in air pollution context, and a point source is a significant producer of emissions within a certain very small location. It's important to understand that when we were measuring just across the street from the gas station, that it could probably be affecting our levels that we were seeing. And this doesn't necessarily affect that particular location that we were looking at, because we're measuring simultaneously inside and outside the shelter, so we're controlling for that point source. But when we compare with the other two shelters, which I didn't really do too much, but at those times when I did, I needed just to acknowledge that, yes, this shelter could be higher. If I see any reasons why it's higher, it's probably because of that point source, or something like that. That came into mostly when I was looking at shelter location relative to the intersection, if it's near side or far side of the intersection. Near side means that it's before the intersection. Far side means it's just after. That shelter happens to be the only far side shelter that I looked at, and so when I was comparing near side versus far side, I did see that far side was higher typically, but that's not necessarily robust because of that point source. Am I still picking?
Yeah.
Over here.
Well, it's kind of a question about your talk also. Do you remember to use the microphone? Touch. Okay. The light's not going on. Okay, I don't think it's any more awkward, but. Is there any data out there that could account for like transit users' behaviors around bus stops, like whether they actually wait inside them or outside them, and what factors influence that?
Not that I have found, although I can just say from us, we had to be there with the equipment the whole time, which was a lot of fun. And we did see that it depended a lot on the weather, not just if it's raining or not, but sometimes even if it's cold, just to get away from the wind. And that's the real reason shelters are built in the first place. That's probably the number one reason, is to shelter from the elements. So when it's raining, we had a lot of people in the shelter, but when it wasn't, or when it was a little warmer, generally speaking, they would stand around the shelter, but not necessarily in it.
Does the weather affect the pollution levels?
Good my question.
Sorry.
I'm gonna
Mr. Moore.
Go ahead, Mark.
Does the rain influence the amount of particulate matter?
It does.
In your knowledge?
Yes. Although it depends on the size of the particulate matter. If it's raining heavily, you do need to make a point that it could be affecting the particulates. However, UFP are so small that they generally behave more like a gas, and as such, they are less affected by the rain. Whereas PM10 are more likely to be affected by the rain. Back.
A little bit more about that. What kind of data they gather, and if people who have Bluetooth, like, are they signing some sort of form saying it's okay to gather that data?
It's a good question. Everyone's Bluetooth devices, if Bluetooth is turned on, they're transmitting their number or their location. There's no signing of paperwork or anything, and so to reduce privacy concerns, as soon as that Bluetooth device is read, the device address is immediately truncated. It's not recorded and then truncated, but immediately truncated. And because of that, there's no way for us to track down or go back and figure out who that actual individual person is. And when these readers are active, we get numerous hits on Bluetooth devices.
Give some examples of Bluetooth devices.
Cell phones are the most common Bluetooth device. A lot of people use Bluetooth earbud headsets, especially now with law most recently being passed in Oregon where it requires drivers to be hands-free. And a lot of those Bluetooth devices are wireless and allows the driver to, keep their hands on the wheel, not on the phone. Or cars are a lot of times Bluetooth ready or able. You can use the car's speakers, and they have a microphone built in. Those are the two most common ones. And then, so we just record these readings, truncated, and then add another Bluetooth device, say downstream. If we get a match, we later process that match and determine maybe how long it took that particular person to get from one station to another. Now we are unable to determine how they got there. Did they walk? Did they bike? We can make some judgment calls. Was it a bus full of people? It's hard to say. But it's just another way for us to estimate travel times in corridors, and maybe in the future, origin and destination patterns. But yeah.
For that same project, you gave a good example of how that data can help adjust traffic signals for an incident as far as cars go. I was curious what examples you can think of for how that data could be used to optimize bicycle traffic or pedestrians, and how do you balance car flow versus, say, if you're detecting a huge number of pedestrians?
Well, that's one thing that isn't being recorded real heavily right now is bicycles and pedestrians. It's difficult to get an accurate read on both of those. But if in Surisha's work, she had mentioned last week how they're creating some ways to actually record pedestrians, and then we're looking at ways of storing that. If we can see that there is a high demand of pedestrian activity in certain areas that we weren't able to actually see before, timing plans could be adjusted to give longer indications for pedestrians to cross, say, busy roads. 80 seconds is a good example. The pedestrian traffic going north and southbound with traffic, those particular pedestrian signals are on recall, so they always are on walk whenever the north-south movement is green. But with some of our data, we could maybe start to now see, well, how many times do people actually cross 82nd? Is there a high demand for it? Is there a significant delay? And then with that delay, are people maybe not waiting long enough when the signal actually comes and making a run for it when there's a break? So just being able to have this data and then maybe go out and start actually making some judgment calls. Okay, there's a lot of pedestrian activity in this corridor. Maybe we need to look at retiming it, not just for automobiles, but for pedestrians. And then bikes as well. Having, knowing when there's a large volume of bikes, maybe starting to use particular intersections, we now need to increase, the yellow time to allow them to actually clear the intersection. So.
We have several questions coming in over the web, and we often never get to them. So I'm arbitrarily picking one of them, and this is for Kristi. Is the foundation for this research the reduction of development fees for developers, or would this also reduce the number of parking spaces in the establishment?
So,
are there other potential uses?
well, so specifically we're looking at ITE's trip generation, which estimates the vehicle trips, which is used for traffic impact assessments for the facilities itself. ITE also has a parking generation estimate, which has very similar issues compared to trip generation, but it's not necessarily the same thing. Vehicle trip estimates from trip generation aren't necessarily used for parking generation, but the impact of the context on both trip and parking generation is both there. They're two different studies, though. So Metro and ODOT were interested in funding this study, specifically looking at vehicle trips. I know it's an interest of theirs to also be looking at parking generation, but it is a different a different study.
Sorry. Thank you. Me? For Christina, actually. Concerning, you spoke briefly to the normalization of data, depending upon, I guess, what type of person was using these facilities.
I can barely hear you. I'm sorry.
You were speaking to the normalization of data. Sorry. Right. I just figured that out. Of income or, I guess, family size, how were those taken into account? Because I guess in my imagination, I'm thinking of like a single couple going to eat versus the troop family with all the children. Was that somehow figured into this data?
So we didn't normalize. We just included them in the model, so we accounted for them in the model. We didn't account for household size, although that could be something to look at. And we looked at household income and household vehicle availability, which is the number of autos related to the number of people in the household. So greater than one would be more than one vehicle than there are per person in the household. That was something that we did look at from the household travel survey, but when we were developing the models, we found that the model that we had developed, including household income and vehicle availability, better described the variation than including household size. But that is something that is important to account for.
Adam, I was curious. You said that the mornings were worse than the evenings for the exposure levels. And I can't remember exactly what you said as far as the locations of the stations. Were they all on eastbound pattern or westbound, or what's your thinking as why that would be the case?
So two of the shelters were located on inbound direction for the morning periods, and then one shelter, which also happens to be the shelter that's near the point source, is on the outbound direction. I wasn't able to find any reasonable differences in vehicle volumes for the morning versus the evening. In fact, if I remember right, vehicle volumes are slightly higher in the evening. However, it's hard to make conclusive statements based on that because I was only measuring half of the roadway. So it's really hard to say. But I think that's more of probably an atmospheric issue than it is of a traffic issue.
One last question. Mr. Adam as well. You mentioned that there's sometimes a correlation between traffic flows and different levels. Is there more of a correlation with
I didn't notice anything directly related to wind and vehicles at the same time. I think that you're more likely to see correlations with ultrafine particulates in vehicles than you are with larger particle sizes. UFP are more, I mean, they're all components of vehicle exhaust, but UFP are very sensitive, I guess, to vehicle levels. And generally speaking, we did see more correlation with ultrafine particulates. So when I said sometimes, I was kind of referring to the particulate size.
So let's thank all of our speakers. You'll do us proud next week. And if you're a student enrolled and I didn't check in with you for attendance, check in with you now. Not you were here last week, so you need to be asking a question. And I did. You did last week? So if you want to write one down.
We can give this back to you guys.
Yeah. Jeremy
yeah, totally.
Rothbo, right? Okay.